Hello learners, we are back to our study of mechanics. In the previous two sessions, you have learned about Newton's laws of motion and the finer concepts you should always remember, you should focus on. Now, we will learn how to apply Newton's laws of motion to simple physical problems and solve the problems on motion of objects. So, we begin with application of Newton's laws part 1. This is based on unit 6 of the course BPHCT 131 entitled Mechanics. As you know, it is a first semester course of BSc-G of IGNOU. And the expected learning outcomes for this unit are: for non-fundamental forces, draw free body diagrams, apply Newton's laws to simple problems and uniform circular motion. I will explain in a bit what I mean by non-fundamental forces. The concepts we will cover in this session range from the equation of motion to types of forces, free body diagrams, determining net force on the object, applying Newton's laws of motion. Now, all these concepts can simply not be covered in one session of half an hour. So, today we are going to focus on the equation of motion, the types of forces and free body diagrams. I have already introduced the equation of motion to you in the last two sessions on unit 5. Today I am going to talk about the types of forces around us and how to draw free body diagrams. And in the next sessions, we will determine net force on the object and apply Newton's laws of motion. Now, before we even think of applying Newton's laws of motion, the important point to remember is that these laws apply to point particles. What are point particles, you may ask? You may like to know. You may like to refresh from unit 6 that point particle is an idealized representation of a real body. It's a representation. A point particle is an idealized representation of a real physical body when we neglect its size. So, we neglect the size of an object and treat it as a point particle like this. Instead of the object, we have a point there. Of course, this point is pretty big. You can draw smaller points. You know what a point is from your mathematics courses. So, we neglect the size of the object and treat it as a point particle while applying Newton's laws of motion. First, the thing to remember is that you have to represent all real physical objects as point particles when you start solving problems based on Newton's laws of motion. Now, we come to the next question. How do we apply Newton's laws of motion to the motion of point particles, right? So, remember the equation of motion? We have to solve this equation. F is equal to ma. I have told you there are three variables here: the net force on the particle, its mass and its acceleration. We will be given two of these and we will need to solve for the third. Usually we are given the force and the mass and we find the acceleration, or if we are given the mass and the acceleration, it's a simple arithmetic multiplication to find the force. So let's see what kind of problems we will be solving. So I have already told you how you can use this equation in 3 ways. So if you know m and acceleration A, you can calculate F. If you know m and the applied force, you can calculate A. And if you know F, the net force on the object, and acceleration, you can calculate mass. These are the kinds of problems you will be asked to solve. Recollect from the previous sessions that F here has to be associated with some force law. I had given you examples of the law of gravitation, Hooke's law, and electrostatics, Coulomb's law for electrostatics. So we need to know the force law, and the expression for force on the left hand side comes from the respective force law applicable to the problem. We find the net force on the object, the net force on the object. These are the words to remember. Net force on the object, of course, which is represented as a point particle. Then we substitute it on the left hand side of the equation of motion. And so the next question is, how do we determine the net force applied on an object or point particle? Let me go back to the previous slide. So if we are given the forces and either the mass or the acceleration, and we need to find the other variable, then we need to find the net force on the object. Net force on the object. Okay. So the next question is, how do we determine the net force applied on an object oblique point particle? So object we will represent as a point particle. We will think of the object in Newtonian mechanics as a point particle for the time being. How do we find the net force? Firstly, we have to know all forces acting on the particle. So now we represent the object as a particle and find out what forces are acting on the particle, only on the particle. And then we draw the free body diagram for the particle and determine the net force on it, and then use the equation F is equal to ma to find either mass or acceleration. This is the process which you need to keep in mind always. Find out all forces acting on the particle, draw the free body diagram for the particle whose motion you are considering, for which you want to solve the equation of motion, determine the net force on it, and then use the equation of motion F is equal to ma. So these are the key ideas that you have to always remember while solving problems related to Newton's laws of motion. You have to find forces on the particle, you have to draw the free body diagram, you have to find the net force, and then apply F is equal to ma. Sometimes you will be given ma and you will be required to find F. As I said earlier, it's a simple problem of multiplying a vector by a scalar. So we will not go into those problems. We will tackle somewhat difficult problems where we need to find the forces on the particle and then the net force. What are the types of forces on the particle that you have studied in section 6.2 of unit 6? You have studied about forces around us, many of those. For example, you have studied about contact forces around us, you have studied about long range forces, and in the beginning I mentioned non-fundamental forces, and so you have studied about fundamental forces, which are the forces of gravitation, electromagnetism, strong nuclear forces and weak nuclear forces. Here we will stick to just the force of gravitation because this is a course on mechanics. So the long range forces that we are going to study are just the force of gravitation or gravity. Force of gravity, as you know, is the force exerted on any particle due to the earth. It's the force of gravitation exerted on any particle near the surface of the earth due to the earth. And it is given by the simple law Fg is equal to mg. We have added a small g as a subscript to show that it is the force of gravity. We will be using this force quite a bit in all the problems. It will be pretty much present, and so you have to know that the force of gravity acts on all the particles whose motion we will be considering in the problems that are relevant to your course. So this is one long range force. The other types of forces are contact forces around us. And what are the ones you have studied? Normal force, friction, tension, and the spring force. So what are these forces? I am going to point out the main features of these forces so that you remember them, how to draw these forces. Remember, you have to find the net force on the particle. So you have to draw these forces, you have to see how these forces are being exerted on a particle. What is normal force? It acts between two objects in contact. Remember, when two objects are in contact, the normal force acts perpendicular to the surfaces in contact. When object A, here in this case tire, exerts force on object B, then object B exerts an equal and opposite normal force on A. So normal, as the word goes, is perpendicular. As I said, when object A exerts force on object B, this yellow arrow, then B exerts an equal and opposite normal force on A. B here is the ground, and we have kept a tire on the ground, and the tire is exerting the force on the ground, which is the force of gravity, and the ground is exerting an equal and opposite normal force on the tire. It is the red arrow, and we denote it by Fn, a subscript n to F. Now notice this important thing. It is very important that you remember that normal force is perpendicular to the surfaces in contact. Always remember, normal force is perpendicular to the surfaces in contact. In a minute you will understand what this means, what I mean by this. So here the tire is exerting a force of gravity on the ground, and the ground is exerting the normal force on the tire, which is equal and opposite to the force of gravity, and it is also perpendicular to the forces in contact. So when you want to find out the forces on the tire, there is a force of gravity due to earth, and there is the normal force due to the ground or the floor on which the tire is kept, and if both are equal and opposite, the tire is at rest because the net force on the tire is 0. So we say that normal force is perpendicular to the surfaces in contact, and here in this case, in this example, the surfaces in contact are horizontal surfaces. So the perpendicular is the red arrow. The perpendicular is in the direction of the red arrow, or vice versa. The normal force is perpendicular to the surfaces in contact, right? Now I give you another example. Here I have shown you a child sliding down a hill, or another child sliding down a slide in the playground. So the child is sitting on the sled, and the sled is inclined at an angle theta. to the horizontal. Similarly, the slide is inclined at an angle theta to the ground. So now the object, if the object is sled or the child, then they are not in the horizontal direction. The surfaces in contact are not both horizontal. The sled is at an angle to the horizontal. The slide is at an angle to the horizontal, right? So the normal force is perpendicular to the surfaces in contact, as I have shown by the blue arrow here. So you see, you have to remember that the normal force is perpendicular to the surfaces in contact. Here the surfaces in contact are the sled and the hill. Hill is inclined at an angle theta to the horizontal. So the normal force is not perpendicular to the ground anymore. It is not perpendicular to the ground anymore. Okay? It is perpendicular to the surfaces in contact as shown by the blue arrow. Similarly, the two surfaces are the child and the slide in the bottom picture on the right, and the slide itself is at an angle with the horizontal, at an angle theta with the horizontal, and the normal force is perpendicular. So it's not a straight arrow, it's now a tilted arrow which is perpendicular to the surfaces in contact. So you need to understand this very well. Here again an example of an inclined plane. Now this is a geometrical drawing, so it's easier to understand. And the normal force is perpendicular to the surfaces in contact, which is now the box and the inclined plane. So you see the two situations I have shown you. On the left, there is this box kept on floor, on horizontal floor. Both the surfaces are horizontal. Fn is perpendicular to the surfaces in contact. On the right, you see a box on an inclined plane, and this is the direction of the normal force perpendicular to the surfaces in contact. This is what you always need to remember while drawing the forces on the particle. So what is the expression for the normal force? In this case, this is Fn equal to Fg. So Fn is just mg. In this case, the incline at an angle theta gives us Fn equal to Fg cos theta. We have to resolve Fg. Its component opposite to the normal force, and the magnitude of the normal force is no longer Fg, it is Fg cos theta. Always remember, when the normal force, when it is a problem of an inclined plane, the normal force is equal to mg cos theta, right? You have to remember these. So I have repeated this slide for you. For horizontal surfaces, you have Fn equal to Fg equal to mg, and for inclined surfaces, Fn is equal to Fg cos theta or mg cos theta. This is something you need to remember. So I hope you are clear about how to draw the normal force on a point particle. I have shown you point particles. I have reduced the boxes to point particles. Let's go to the next force, friction around us. Again, friction is also exerted when two objects are in contact, and you see it around you. Because of friction, you are able to walk. You try walking on a slippery road, you will feel the need for friction. Swimming, when you swim against water, you need to overcome the resistance due to water. That is also an example of friction. So friction is a force which is directed along the surfaces in contact. Unlike the normal force which was perpendicular to the surfaces in contact, friction is along the surfaces in contact and opposite to the direction in which the object moves or attempts to move. See, along the surfaces in contact, opposite to the direction in which the object moves or attempts to move. So when object A moves or attempts to move along the surface of another object B, a force of friction is exerted on A. And as I said, friction is very necessary in our lives. You see, you try walking on icy roads or wet roads, you will really feel how important it is. It is important to overcome friction in many cases, but friction also helps us in many ways. What you need to remember is that it acts along the surface, opposite to the direction of motion. There are two kinds of forces of friction, static friction and kinetic friction. Let's first talk about static friction, which is exerted between objects at rest or about to move with respect to each other. So you have, for example, a box on a floor, and when you try to move that box and it does not move, this means that a force of static friction is being exerted on the box. And the magnitude of the force of static friction can have any value from 0 to a maximum value, depending on the force you are exerting on the object. Fs maximum is equal to mu s Fn, where mu s is the coefficient of static friction and Fn is the normal force. This is the maximum force of static friction that can be exerted on any object. So for example, you are pushing a heavy almirah and it doesn't move. Why doesn't it move? You are applying a force on it, but it's not moving because of static friction. You see the black arrow there with Fs written next to it? You are pushing the almirah. The force of static friction is acting opposite to the direction of motion and the almirah is not budging. So you apply more force on it, somewhat more, and as it starts to move, the force of static friction is maximum. It is maximum just as the almirah starts to move, and when it is set moving, the force of kinetic friction comes into play. Suppose you are pulling the almirah, pulling the heavy almirah. Which direction would the force of static friction point in? It's now opposite, because the almirah is now being pulled towards you. So it is now opposite. The black arrow is in the opposite direction to the direction of motion, right? So you have to be careful about drawing the force of friction, static as well as kinetic. Kinetic friction is exerted between objects moving or sliding with respect to each other. So these two arrows show you the direction of the force of kinetic friction. When this object is sliding towards you, the force is opposite. When it's sliding away from you, the force is towards you. The force of kinetic friction opposes the motion of the object. Let me show you once again. Now, what is the expression for the force of kinetic friction? It is Fk is equal to mu k Fn. Fn, as you know, is the normal force and mu k is the coefficient of kinetic friction. This expression you will need to remember. So, the force of kinetic friction Fk is exerted opposite to the motion of objects moving with respect to each other. Here the blue arrow shows you the direction of the force of kinetic friction. As the box moves to the right, there is a force to the left. As the box moves to the right, Fk equal to mu k Fn is exerted to the left, right? We could put it in a loop and you could understand this. So always opposite to the direction of motion. Another example, the box is coming down, it is sliding down. The black arrow shows you the direction of the force of kinetic friction, which is equal to mu k Fn. Fn here would be mg cos theta, as you may remember. Now if you are pulling the box up the inclined plane, then again Fk is opposite to the direction of motion. So it is shown by the black arrow here. Fk is equal to mu k Fn. So always draw the force of kinetic friction opposite to the direction of motion of the object. So always remember that the force of friction acts in the opposite direction to the object's motion. Then we come to another force around us, the force of tension. Tension, as you know, is the force exerted on an object when we pull it by a rope, cable, string or any other cord attached to it. It is directed away from the object and along the cord. This is what you have studied. So what is the force of tension here? This red arrow shows the tension in the cord. The object is the car and it is being pulled, so the force is along the direction in which the car is being pulled, along the cord attached to the car, along the rope attached to the car. This is a stunt you may have seen many times around you. Then the spring force, again you have learnt about it. When you attach a spring to an object and compress or stretch the spring exerts the spring force upon the object. What is the expression for the spring force? It is given by Hooke's law. F is equal to minus kx. Remember always, the spring force tries to restore the object to its rest or equilibrium position. That is why the sign minus comes there, and it is because of this that the spring force is called the restoring force, and K is the spring constant, which is the property of the spring. You've read about it in section 6.2.4 of unit 6. So in this session we have covered 4 types of forces: the normal force, friction, tension and spring force. The next step is to solve the equation of motion F is equal to ma for a particle. So on the left side, as you have seen, the force in this equation could be normal force, friction, tension or spring force or any combination of these forces. So on the left hand side, depending on the types of forces acting on the particle, you have to write, instead of F, the expressions. If it's normal force, you have to write Fn. If it is friction, you have to write the force of friction, tension or spring force. I have already explained the expressions for each of these types of courses. So with this, we come to an end of this session. In the next session, I am going to explain to you how to solve the equation of motion F is equal to ma. Let me quickly deal with the basics of that. You have to, as I have told you earlier on in the program, identify all forces applied on the particle, draw the free body diagram for it in an inertial frame of reference, calculate the net force on it. And this is explained very well in the text box on page 36 of section 6.3 of unit 6. This is what I am going to take up in my next session on unit 6 on applying Newton's laws of motion to the motion of particles. So to summarize, in this session we have explained the various types of contact forces around us. normal force, friction, tension and spring force. In the next session, we will explain how to solve the equation of motion when one of these forces or a combination of these forces is being applied on a particle. Until then, happy studying Unit 6.